How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You're at a birthday party. The cake comes out, candles blazing. Your friend is laughing, face illuminated by the warm, flickering light. You pull out your phone, frame the shot, and tap the button. Click. In that instant, the moment is saved. The smoke rising from the extinguished candles, the specific shade of joy on your friend's face, the glint of the frosting. It's all there, perfectly preserved, ready to be shared with the world in seconds. We perform this little miracle dozens, maybe hundreds of times a week. It is so deeply woven into the fabric of our lives that it has become utterly mundane. We document our food, our children, our pets, our travels, our moments of quiet beauty and raucous celebration. The act is as reflexive as breathing. We point, we tap, and reality is captured. It feels direct. It feels true. We assume the camera in our phone is a tiny, perfect window. It opens its eye for a fraction of a second, sees exactly what's in front of it, and saves that vision as a file. Simple. But have you ever truly stopped to wonder how that actually works? What is the bridge between the physical world of light and the abstract world of data? How does a machine convert a fleeting analog phenomenon, a photon that has traveled 93 million miles from the sun, bounced off your friend's face, and entered a tiny lens, into a structured digital thing made of ones and zeros? What are the fundamental rules, the first principles, that make this magic trick possible? Because when you look closer, it isn't a simple window at all. It's a sophisticated lie. A beautiful, convincing, and incredibly useful lie. And the story of how that lie is constructed is far more fascinating than the simple magic we take for granted. Today, we are opening the black box. We're going to deconstruct one of the most common, yet most misunderstood pieces of technology on the planet: the digital camera sensor. The sheer scale of digital photography is difficult to comprehend. Every 2 minutes, humans take more pictures than existed in total 150 years ago. Trillions of images are created every single year. The smartphone has put a high-quality camera into the pockets of billions of people, fundamentally changing our relationship with memory, art, and communication. It's the most prolific device for capturing our world that has ever existed. The magic we see is intoxicating. We can shoot in near total darkness, and our phones produce an image that is brighter and clearer than what our own eyes could perceive. We can tap on a face and have the background instantly blur into a beautiful creamy wash, mimicking a professional camera with a giant lens. We can capture video in stunningly high resolution and slow it down to see a hummingbird's wings beat or a water balloon burst. This technology has dissolved the barriers of the old world. There's no film to buy, no limit of 24 or 36 exposures. There's no waiting, no darkroom, no chemicals. The loop between capturing a moment and sharing that moment has been compressed to nearly zero. This effortlessness is the hallmark of truly transformative technology. It's so good, it has erased any thought of how it works. It has become an extension of our own eyes and memory. But to appreciate the genius of it, we have to rewind the clock. We have to go back to a time when capturing light was a messy, cumbersome, and deeply physical process. Before the digital sensor, there was film. For over a century, photography was chemistry. It was an intricate dance of light and silver. A piece of film is a plastic sheet coated with an emulsion containing microscopic crystals of silver halide. When light strikes these crystals, it triggers a tiny chemical reaction, creating a few atoms of metallic silver. It's an invisible change, a latent image. You can't see it yet, but the information is there, stored as a chemical potential. To reveal the image, you had to take the film into a darkroom and bathe it in a series of chemicals. A developer turns the exposed silver halide crystals into visible black silver, making the image appear. A stop bath halts the development process. A fixer washes away the unexposed crystals, so the film is no longer sensitive to light. It was a craft. It took time, skill, and money. Every single picture had a cost attached, not just in film and chemicals, but in effort. You had to be deliberate. You had to think before you pressed the shutter. The core problem, the one that drove engineers for decades, was this: how do you get rid of the chemistry? How do you create a reusable electronic version of film? How do you capture light not with silver, but with silicon? The goal was to build a machine that could see. This wasn't just about taking pictures of birthdays. The quest for an electronic eye was driven by everything from broadcast television and spy satellites to factory automation and video phones. The breakthrough came, as it so often does, from a place of serendipity. In 1969, at the legendary Bell Labs in New Jersey, two physicists named Willard Boyle and George Smith were brainstorming. Their assignment wasn't to invent a camera. They were trying to create a new kind of computer memory. Their idea involved creating a device where you could inject a packet of electrical charge at one end and then shuffle that packet along a line of tiny electronic gates to the other end, like passing a bucket of water down a line of firefighters. They called it a charge-coupled device, or CCD. During their brainstorming session, which they claimed took about an hour over lunch, they had a realization. What if, instead of injecting a charge with a wire, you used light to create the charge? They knew about a strange property of certain materials, a phenomenon that science was still grappling with. They knew that light, under the right circumstances, could create electricity. If they could use that effect to create the initial charge packets, their device wouldn't just be a memory device. It would be an imaging device. Each little bucket could store a charge proportional to the amount of light that fell on it. They had, on a blackboard in an office in New Jersey, sketched out the fundamental architecture of the digital camera sensor. It was so elegant, so revolutionary, that they would eventually win the Nobel Prize in physics for it. But it was just a concept. The first person to actually build a working digital camera was a young engineer named Stephen Sasson, working at Kodak in 1975, the very company that dominated the world of film. His device was a beast. It was the size of a toaster, weighed 8 pounds, and was a tangle of circuit boards and wires. To capture an image, you had to hold it still for 23 seconds. It recorded a grainy 0.01 megapixel black and white image onto a digital cassette tape. To see the picture, you had to take the tape and put it into another custom-built machine that would display it on a television. Sasson showed his creation to the executives at Kodak. They were intrigued, but they asked him a crucial question. Why would anyone ever want to look at their pictures on a TV? They couldn't see past the world they had built, a world of paper prints and family photo albums. They saw this new technology not as an opportunity, but as a threat to their incredibly profitable film business. And so, they buried it. Kodak, the company that invented the first digital camera, would decades later be bankrupted by it. A classic tale of the innovator's dilemma. But the idea was out. The bridge from light to numbers had been built. It would just take a few more decades of miniaturization and refinement for it to end up in your pocket. So let's open the box. Let's look inside your phone, past the battery and the logic board, at that tiny square of silicon that actually sees the world. At its heart, the principle is the one Boyle and Smith sketched out. It's an array of buckets. To understand this, let's use an analogy. Imagine you want to create a map of a rain shower. You could go out into a massive field and lay down a grid of millions of identical, tiny rain gauges or buckets. Let's say 1,000 rows of 1,000 buckets each. Now, a brief complex rainstorm passes over. It rains harder in some spots, lighter in others. After exactly 1 minute, you magically put lids on all 1,000,000 buckets simultaneously. To create your map, you would then walk to each bucket in order and measure the amount of water inside. Bucket at row 1, column 1, 5 millimeters. Bucket at row 1, column 2, 5.2 millimeters. Bucket at row 1, column 3, 3 millimeters. You would record all these measurements in a giant spreadsheet. What you would have is a grid of numbers. If you then converted those numbers into shades of gray, more water equals a darker square, less water equals a lighter one, and displayed them on a screen, you would see a picture. You would see a map of the rainfall. You would have captured an image of the storm. This is precisely what a digital camera sensor does. The field is the silicon sensor. The buckets are called photosites, and there are millions of them, each destined to become 1 pixel in your final image. And the rain, of course, isn't water. It's light. Specifically, it's made of tiny individual particles of light called photons. When you take a picture, the camera's shutter opens for a specific amount of time, say 1/60th of a second. During that interval, photons from the scene you're photographing stream through the lens and bombard the sensor. The bright parts of your scene, like a sunlit cloud, send a torrent of photons. The dark parts, like a deep shadow, send only a trickle. Each photosite, each bucket collects these photons. But this raises the first critical question. A bucket can collect water. How does a tiny square of silicon collect light? Light is ethereal. It has no mass. You can't trap it in a box. This is where the story moves from simple mechanics to the beautiful weirdness of quantum physics. This is where we find our first principle. The secret lies in a phenomenon that was so strange, so counterintuitive when it was discovered, that it baffled scientists for years. It's called the photoelectric effect, and the man who finally figured it out was none other than Albert Einstein. In 1905, his miracle year, Einstein published 4 groundbreaking papers. One gave us $E equals mc squared dollar, and the theory of special relativity. Another provided evidence for the existence of atoms. But the paper that would actually win him the Nobel Prize was the one on the photoelectric effect. For decades, physicists had known that if you shine a light, particularly ultraviolet light, onto a piece of metal, it can create a spark. It was somehow knocking electrons loose from the metal's atoms, creating an electrical current. But the details were bizarre. According to the wave theory of light, a brighter light, a more intense wave, should knock out electrons with more energy. But it didn't. It just knocked out more electrons. To get more energetic electrons, you had to change the light's color, its frequency. A dim blue light could knock electrons loose when a bright red light did nothing at all. It made no sense. Einstein's radical proposal was to take seriously the idea that light wasn't just a continuous wave. It was also a stream of discrete energy packets. Like tiny bullets, he called these packets quanta, and we now call them photons. His theory stated that each photon carries a specific amount of energy determined by its color. Blue light photons carry more energy than red light photons. Now, Picture an atom in the silicon sensor. It has electrons orbiting it. To knock one of these electrons free, you need to hit it with enough energy. Think of it like a coconut shy at a carnival. You need to throw the ball hard enough to knock the coconut off its perch. A low-energy red photon is like a soft throw. You can throw thousands of them, and the coconut will just wobble. But a single high-energy blue photon is like a fastball. It has enough energy in one packet to knock the electron clean out of its orbit. This is the photoelectric effect. One photon goes in, one electron comes out. It is the fundamental transaction at the heart of every digital camera. It is the bridge that connects the world of light to the world of electricity, and it's a beautifully simple relationship. The more photons that hit the photosite, the more electrons are knocked loose and trapped inside it. So, let's go back to our rain gauge analogy. Our silicon buckets aren't collecting photons directly. They are collecting the electrons that the photons dislodge. During that 1/60th of a second, the shutter is open. The photosites are active. A bright area of the scene sends a flood of photons, which liberate a large number of electrons that are then collected in the corresponding bucket. A dark area sends only a few photons, so its bucket collects only a handful of electrons. When the shutter closes, the collection stops. The sensor now holds a pattern of stored electrical charge. Each of the millions of photosites contains a different number of electrons, a faithful representation of the brightness of that specific point in the original scene. The next step is the readout. The camera's processor systematically goes to every single bucket and measures its electrical charge. It's like a microscopic census taker going door to door. It converts each analog charge level into a digital number. A bucket that is completely full of electrons might be assigned the maximum value, say 4095. A bucket with no electrons gets a 0. Everything in between gets a corresponding value. At the end of this process, what we have is a massive grid of numbers. A 12-megapixel camera produces a grid of roughly 4,000 by 3,000 numbers. This is the raw data from the sensor. If we were to map these numbers to grayscale values, we would have a perfect high-resolution black-and-white photograph. We have successfully converted light into a digital file. But of course, our world is in color, and this brings us to the next and perhaps most ingenious part of the story. Because there's a problem. Our sensor, our beautiful grid of light-sensitive buckets, is colorblind. A photosite can only count how many electrons were knocked loose. It has no way of knowing if it was hit by a low-energy red photon or a high-energy blue photon. It only measures total intensity. It can tell you how much light it saw, but not what kind of light. This is where one of the most common misconceptions about digital cameras arises. We intuitively assume that each pixel on the sensor captures the full color of the light hitting it, just like our eyes seem to. This is not true. Not even close. The raw reality is that every single pixel on your camera sensor captures information about only one color. So how do we trick this colorblind device into seeing a full-color world? The solution is both incredibly clever and surprisingly low-tech. We use a filter, specifically a microscopic mosaic of color filters that is laid directly on top of the grid of photosites. This is the Bayer filter, named after its inventor, Bryce Bayer, another Kodak scientist. Imagine going back to our field of rain gauges. Now, before the storm, we place a tiny piece of colored cellophane over the opening of each bucket. We do it in a repeating pattern. Over the first bucket, a piece of red cellophane. Over the bucket next to it, green. Below the red one, another green one. And next to that one, a blue one. Red, green, green, blue. We repeat this 2x2 pattern over the entire field of millions of buckets. Now, when the rainstorm of photons arrives, each bucket can only be filled by light of a specific color. The bucket under the red filter only collects red photons and measures their intensity. The buckets under the green filters only measure green light's intensity, and the one under the blue filter only measures blue light's intensity. You might notice there are twice as many green filters as red or blue. This is done on purpose to mimic the human eye, which is most sensitive to green light. After the exposure is finished and the charge is read out, we don't have a single grid of numbers anymore. We have a patchwork quilt. We have the exact brightness value for red at 1 pixel location, but we have absolutely no information about the green or blue light at that same spot. For its neighbor, we know the precise green value, but have no idea about its red or blue values. This raw data file, this colorful mosaic of incomplete information is not a pretty picture. It looks like a noisy, grid-like mess. So, how do we get from this gappy, incomplete data to the smooth, full-color photograph you see on your screen? This is where the camera ceases to be a simple measurement device and becomes a powerful supercomputer. The camera's brain, its dedicated image signal processor or ISP, performs an astonishing act of computational magic. The technical term is demosaicing, or sometimes debarring. But what it really is a highly sophisticated guessing game. The processor looks at a single pixel, let's say a red one. It knows its own red value perfectly, but it needs to figure out the green and blue values for its exact location. To do this, it looks at its neighbors. It sees the values from the green pixels directly above, below, left and right of it, and it takes an average. It says, okay, the green light in this immediate neighborhood seems to be about this bright, so I'll assume the green value right here is that average. It does the same thing for blue, looking at the blue pixels at the corners around it and interpolating a value. It performs this act of inference for every single pixel in the image. For a green pixel, it looks at its red and blue neighbors to guess its missing values. For a blue pixel, it looks at its green and red neighbors. This happens millions of times in a fraction of a second, governed by incredibly complex algorithms that have been refined over decades. These algorithms are smart. They don't just take simple averages. They look for patterns, for edges, for textures, to make their guesses more accurate and avoid creating strange color artifacts or blurring. Think about what this means. The final, full-color image you see on your phone is a reconstruction. It's a fabrication. For any given pixel, 2/3 of its color information is not directly measured. It's intelligently inferred. The camera is using math to fill in the blanks, to create a plausible and beautiful version of reality from incomplete data. It's not a window. It's a masterful portrait artist, painting a picture that looks real, but is ultimately a product of its own interpretation. The fact that it works so well, that the results are so seamless and convincing, is one of the great triumphs of modern engineering and computer science. Now, you might think the story ends there. We've journeyed from photons to electrons via the photoelectric effect. We've seen how a grid of photosites captures the intensity of that electrical charge, and we've uncovered the clever trick of the Bayer filter and demosaicing that turns a colorblind sensor into a full-color camera. This is the core of how a digital camera works. But in the world of modern photography, especially in the phone in your pocket, this is just the beginning. The processing doesn't stop at guessing the colors. And that leads us to the unseen giant of digital imaging, the true source of the magic we see today. The data that comes out of the demosaic process, the so-called linear image file, still doesn't look like the final photo you post on Instagram. It often looks flat, a little dull, and not very contrasty. The real secret sauce, the thing that separates an okay camera from a great one, is what happens next. The image signal processor embarks on a whole new set of adjustments, a computational ballet that transforms the raw data into a visually pleasing photograph. First, it does noise reduction. At a microscopic level, the sensor is a noisy place. Sometimes, thermal energy or random quantum fluctuations can knock an electron loose, creating a signal where there was no light. This appears as a grainy, speckled pattern, especially in dark photos. Sophisticated algorithms identify this noise and smooth it out without destroying the actual detail in the image. Next, it applies sharpening. The Bayer filter interpolation, by its very nature, can soften an image slightly. So, the processor runs algorithms that look for edges, the boundary between a dark object and a light background, for instance, and increases the contrast right along that edge. This creates the perception of a sharper, more detailed image. Too much of this, and the photo looks artificial and crunchy. Just the right amount, and it looks crisp and clear. Then comes color and tone mapping. The sensor captures a much wider range of brightness than a screen can display or a print can reproduce. The processor has to make choices. It has to compress that range, deciding how to map the deep shadows and the bright highlights into the available palette. It also adjusts the overall color balance, making sure whites look white and skin tones look natural. And this is where the look of a particular brand of camera comes from. This is the real aha moment of modern photography. When you take a photo with an iPhone versus a Google Pixel versus a Samsung Galaxy, you're not just comparing their lenses or their sensors. You are, more than anything, comparing their philosophies of what a good picture should look like. The engineers and computer scientists at Apple have a certain aesthetic taste. They write their processing algorithms to produce images that are often described as natural, balanced, and true to life. The team at Google might favor a different look, often more dramatic, with higher contrast and more apparent sharpness, a style born from their pioneering work in what's called computational photography. Think of it like this. The sensor and the lens provide the raw ingredients for a meal. They capture the photons and turn them into a set of numbers. But the image signal processor and its software are the master chef. The chef takes those raw ingredients and decides how to season them. How much salt, sharpening, how much spice, color saturation. How should it be cooked, tone mapping. Two world-class chefs given the exact same basket of ingredients will produce two very different but equally delicious dishes. This is the unseen giant, the software. It's why your tiny smartphone, with its impossibly small lens and sensor, can create images that rival dedicated professional cameras from just a decade ago. It's cheating. It's using computational power to overcome physical limitations. Consider something like portrait mode. When you enable it, the phone doesn't just take one picture. It often uses two separate cameras to create a depth map, figuring out what's close to you and what's far away. Then, it uses sophisticated AI algorithms, trained on millions of images, to identify the person in the foreground and meticulously cut them out. Finally, it applies a digital blur to the background, simulating the look of a wide-aperture lens. The final image is a composite, a computational collage of multiple data sources and algorithmic decisions. Or think about night mode. In a dark scene, the phone doesn't just take one long exposure, which would be blurry if you moved at all. Instead, it takes a rapid burst of many shorter exposures. Some of these frames might be blurry, some sharp. The software analyzes the burst, aligns the sharp parts of each frame, intelligently merges them to average out the noise, and brightens the result to create a single, clean, and surprisingly bright photograph. You aren't capturing a moment. You are capturing a range of moments, and the software is rebuilding a better version of reality from the pieces. So we've been on quite a journey. We started with the seamless magic of tapping a screen and saving a memory. We assumed it was a simple window on the world. But when we pried it open and looked at the first principles, we found something far more complex and fascinating. We found that the entire process rests on a peculiar piece of quantum mechanics that Albert Einstein figured out over a century ago. The photoelectric effect, the fundamental law that allows light to become electricity. We found a marvel of engineering in the sensor itself, a vast grid of microscopic buckets, each designed to collect the electrons liberated by light. A silent, solid-state replacement for the messy chemistry of film. We uncovered the ingenious trick of the Bayer filter, a microscopic mosaic that allows a colorblind sensor to see the world in vibrant color, and the powerful computational engine that intelligently guesses the missing two-thirds of the image data to create a seamless whole. And finally, we saw the hand of the artist, the unseen software that sharpens, color corrects, and stylizes the final image, embedding the aesthetic choices of its creators into every photo you take. The first principle of the digital camera, then, is not just that light can be turned into numbers. It's that a photograph is not a simple recording of reality. It's an active and incredibly sophisticated reconstruction of it. The device in your hand doesn't just see the world. It measures it, deconstructs it into millions of individual data points, the brightness of a single color in a single location, and then, guided by the rules of physics and the artistry of its software, it rebuilds a version of that world for you. So the next time you raise your phone to capture a sunset, a smile, or a fleeting moment, take a second to appreciate what is actually happening. You are not merely holding a camera. You are holding a tiny physics laboratory, a high-speed supercomputer, and a digital artist, all working in concert in the sliver of a second it takes to press a button. It's a device that doesn't just capture our reality, it interprets it, preserving not a moment as it was, but a moment as the machine believes we want to remember it.
You've been listening to First Principles. Until next time, stay curious.